Ever wondered how AI models like GPT or BERT understand language so profoundly? It's not magic. It's a blend of mathematical elegance and computational power. Today, we're diving deep into the architecture of transformer models, the backbone of modern NLP. Buckle up, because we're unpacking the mechanics of self-attention, positional encoding, and why these systems outperform their predecessors in ways that'll blow your mind. Let's start with a crash course on why traditional models like RNNs and LSTMs fell short. These architectures process text sequentially, which meant they struggled with long-range dependencies, like remembering context from 100 words ago. They also couldn't parallelize computations, making training slow and inefficient. Enter transformers, introduced in 2017 by Vaswani et al. Inattention is all you need. This paper didn't just tweak existing models. It redefined the paradigm by replacing recurrence with self-attention mechanisms, enabling massive parallelization and capturing global dependencies. But how exactly does that work? Imagine you're reading a sentence and trying to understand how each word relates to the others. Self-attention is the model's way of doing the same. Here's the math. For every word in a sequence, the model computes 3 vectors, queries, keys, and values, using learned linear transformations. The attention score between 2 words is the dot product of their query and key vectors, scaled by the square root of the key dimension. This score determines how much focus the model places on one word when encoding another. The final output is a weighted sum of the value vectors, where weights are the softmax of these scores. It's like the model dynamically assigns importance to different parts of the input, creating a rich, context-aware representation. But wait, how does the model know the order of words? Unlike RNNs, transformers don't process text sequentially. To encode position, researchers introduced positional encodings, which are added to word embeddings. These encodings use sine and cosine functions of different frequencies, allowing the model to learn relative positions. For example, the positional encoding for position I and dimension d is pi 2k equals sin I slash 10,000 2k slash d. Pi 2k plus 1 equals cos I slash 10,000 2k slash d. This ensures the model can distinguish between cat sat on the mat and mat the on sat cat, even though it's not processing them in order. It's a genius workaround that preserves sequential information without recurrence. Now let's talk about the architecture. A transformer consists of an encoder and decoder, each made of multiple layers. Each layer has 2 sublayers, self-attention and a feed-forward network. The self-attention sublayer allows the model to weigh input elements, while the feed-forward sublayer applies nonlinear transformations. Between these, there are residual connections and layer normalization to stabilize training. The decoder also includes an additional attention layer to focus on the target sequence, enabling tasks like translation. This stacking of layers allows the model to capture hierarchical patterns, from individual words to syntactic structures to semantic meanings. Transformers aren't just smarter, they're faster. By eliminating recurrence, they leverage GPUs to process entire sequences in parallel, slashing training time. This scalability is why models like GPT-3 and BERT can handle billions of parameters. But there's a catch. The computational cost of self-attention grows quadratically with sequence length. That's why researchers are now exploring optimizations like sparse attention or linear attention mechanisms to make transformers viable for longer texts. So what's next? Transformers are already revolutionizing NLP, but their impact extends beyond language. They're being adapted for vision transformers, biology AlphaFold, and even reinforcement learning. The key takeaway: the transformer's ability to model complex relationships through self-attention is a paradigm shift. As researchers refine these models, whether through efficiency gains or hybrid architectures, the possibilities are limitless. If you're curious about the math behind the magic, check the description for papers and resources. Thanks for watching. Now go explore the world of transformers and see how they're shaping the future of AI. Like this video. Subscribe for more deep dives into AI research. Questions? Drop them in the comments. Until next time, keep learning. And remember, the next breakthrough is just a few equations away.